Hello and welcome to IoT Builders. This is a live stream where we discuss a range of topics on the Internet of Things, starting from embedded devices to cloud services, all from an IoT Builder perspective. So it is December 14th, and this is episode 13 of our weekly live stream. And today we have a special guest, James Munns, who is managing director of One Variable, or how he likes to call himself, chief whiteboarding engineer. My name is Nenad Ilic. I'm a senior developer advocate for AWS IoT, and I'm joined with my colleagues and co-hosts. Dan, are you on the line?
Hey, Nenad. Yeah, I'm here. I'm glad to be able to join. Thanks for hosting IoT Builders this week.
Yeah, yeah. Thank you for letting me. So awesome. And yeah, we have James. James, are you able to speak? Can you hear us? Is the line okay?
Yeah, I can hear you. Hopefully I'm coming in clear as well.
Yes, perfect.
I'm seeing subtitles, so I'm guessing so it's working okay.
Yeah, excellent. Excellent. So maybe, yeah, so welcome to our IoT Builders show. And maybe you can start by introducing yourself.
Sure. Yeah, I'm James Munns. I do a lot of embedded development stuff. Right now I'm running a solo consultancy called One Variable UG, where I'm helping a lot of people with a lot of different things, basically anything that I can help them with. I spend a lot of time working on either bare metal embedded systems or just helping out with larger, more challenging projects, things that involve hardware and software, and working on the planning and systems engineering side of that, and doing a lot of Rust, I think entirely Rust these days, on both embedded systems and not embedded systems.
Well, that's pretty cool. And I think we also have Syed joining. Syed, welcome. I think you can speak now. Let me know if that works.
Yeah, hi. Sorry, I overran on my other meeting. Yeah, so just an introduction, just like Dan and Nenad here. I'm a developer advocate in the IoT service team, and good to have you over here, James, to speak with us. Thanks.
Excellent. James, I think you mentioned the systems engineering. This is a topic I'm generally interested in, and you and I, we work together a bunch of occasions, and I really like this approach. So maybe you can tell us more about this.
Yeah, I think this came up because I wrote a post about it recently where I haven't had a good and succinct way of explaining systems engineering to people, and there's definitely like the NASA standard definition, and there's probably even an IEC or whatever standard definition for systems engineering. But for me, it's sort of thinking about what you're building and how you're building it. And they seem like pretty simple topics. And for smaller projects, they are. They're usually, something that someone can keep in their brain and keep track of everything that's going on and bring it from start to finish. But for a lot of projects, especially projects that span multiple domains, so embedded systems in particular, or IoT, where you have sort of the hardware aspect of it, you've got the firmware aspect of it, maybe the back-end software, or even the user application or web application and things like that. It becomes a problem that's too big for one person most of the time to solve entirely on their own, which means that you end up having to split the work up and split the problem up, not just across different pieces of what you're building, but really keeping an eye on what is the whole system doing, or how do all of these parts click together, and how do we keep track of all of them? And then during development, how do we keep all of those things moving and know that we're working on the right things? And when we finish one piece, how can we be fairly confident that when we plug it into something else, it's going to work and not end up in the place where two people were building something totally separately, and when you plug them together, they fall over, which is not necessarily what you want to happen. So I know you and I worked we've worked together before, particularly in places where we have to do either things like rapid prototyping or integrating with an existing complex system that we have to communicate with and work alongside with. And I've realized sort of over those years that keeping track of what you're trying to do is a fairly important thing, especially the larger the scope of the project and the more critical it is to get right the first time.
Yeah. Can you give an example on like how you capture this? Like, what are the tools that you use to capture all of this? I'm just curious.
Yeah, it's interesting. So my original work background is in the more safety critical fields. So I started my career doing avionics, so developing firmware for airplane electronics. And there's a really formal approach to that. And depending on which safety critical industry you're in, there will be a different one. But in avionics, software follows DO 178C, which is basically a guide of how you're supposed to be doing things. And it covers things like how you write requirements and how you write your code and how you do testing and how you prepare all of your documentation and stuff like that. And then I had a fairly rude awakening when I left aviation and started working actually more actively in the IoT space and realizing, and particularly for startups, and realizing that those industries don't have a lot of those things. Yeah, nobody does that. And I think it was a pretty big culture shock for me because I sat down at the first project and went, but it's not specified what we're supposed to do anywhere, and where do we do all of this stuff? And surprisingly, in a lot of places, the answer is either we don't, or it's handled through some other framework of thinking of things. And that's something that I find a lot of the clients that I work with or have worked with over the last couple of years also really struggle with, because they're sort of in degrees or self-taught folks. You learn how to break a problem down because that's sort of a thing that's native to software of like, okay, well, this is going to take these functions, or I'm going to break this up into classes or modules or whatever makes sense for the language that I'm using. And you think, okay, yeah, I have to deconstruct the problem. And that's something that works really well on pure software projects where you go, okay, I'm just going to break this down into different pieces of software. But especially once you get things like hardware involved, or you've got the firmware folks talking to the backend folks, and they have wildly different tools and practices that they're using, or even languages that they're using to solve problems, you get sort of lost in the different areas. So the answer is, there haven't been some wonderful off-the-shelf tools that I found that can get you that sort of benefits that I saw from working at safety critical companies, where they either are using a really expensive tool to track all of these things, or they've built some in-house tool that was really expensive because they had a team working on it for years and years to make it right. But one of my favorite books, so Koopman, who's the guy that did the analysis of Toyota when they had the unintended acceleration. He has a book called Better Embedded Systems Software, which sounds like it's really specific to embedded systems, and it has a lot of stuff for embedded systems in it, but it's also one of the best breakdowns of like introduction to systems engineering topics of like, one of his go-to sayings there is, you should have just enough paper, which means you should have enough documentation and process so that it helps, but not so that it becomes some like huge tedious thing. And so when I get brought into clients and stuff like that, and sometimes they're like, we're building something from scratch, and I go, what are you building? And they go, and they throw maybe like one page of marketing copy at me. Or a lot of the times I help folks who are either porting stuff from Rust, or for the next generation of their product, they're looking to move from some other language to Rust. And I go, great, well, before we re-implement this or whatever, I need to know what we're building. Do you have some requirements or some architecture documents or a description of what the system does? And they go, well, we have the code. And I'm like, it would take me a long time to distill your thousands of lines of C or Python or whatever language into requirements. And a lot of the time the answer is just use whatever is helpful. So a lot of the times I just use Markdown, and I'll throw things in a Git repo, and that's great because it means that it's version controlled, and Markdown is pretty easy to track changes on. And once we have sort of a more working base case, like we've captured most of the stuff, we can start using regular Git workflow with that, where you say, okay, someone either needs to fix the requirements because they're not quite right, or someone wants to propose something new, and we can go, great, yeah, just open a pull request that has that in there. So whatever tools, there's no one right tool, but whatever you have at hand and everyone knows how to use, you can set up with not a lot of effort, but just enough formality, if that makes sense.
Yeah. No, it makes perfect sense. Yeah. And to add to this, like from my experience, I think, those kind of like so-called alignment meetings where you actually do whiteboarding sessions where you capture things either through like, boxes and lines, is also something that's like really beneficial to, align the team or like what is actually been done so far and like where needs to go as well. I'm not sure what your experience is this. Like, I know we were joking about you being like a, chief whiteboarding engineer. So that's why I'm kind of like asking this as well. I assume it's kind of like similar, apart from like putting things in Markdown, is like, doing drawings as well.
Yeah, for sure. So, I mean, like that's sort of the catch, is that like systems engineering is usually tracking the progress or like what the system as a whole is doing. So it's one of those things where it's great to be able to sit down with some people on your team and be able to draw things out on the whiteboard, because that kind of communication gets everyone on the same page.
Yes.
And when everyone understands what the big picture is, they're more likely to build the individual responsibilities that they have, or the individual components that they have, in a way that will fit into that bigger picture. But that's actually where a lot of these teams fall down, is they had this conversation 6 months ago, and everyone was on that page 6 months ago, but no one captured that anywhere or made that, official or
trackable.
Or even just they had the conversation with the 3 people in the room, but someone was on vacation, or the hardware folks are in another office or something like that. And so they have a good picture of it in their brain, or they think they have a good picture of it in their brain, but whoever wasn't in that conversation in the room at the time might not be. So a lot of this is having those conversations and then capturing them into somewhere where everyone can see it, because the goal is that no one has to guess how the system works. That you can always say, well, I'm building this part and this person's building that part. How do they click together? Instead of having to guess, you go, well, did we write down how they're supposed to click together? And can we,
like what are the interfaces?
Can I go look at the docs to tell me what the interfaces are? Exactly, yeah. Or if you start building and you go, wait a minute, what we had planned originally isn't going to make sense, or it's not the best way of doing things, then you have one place where you go, hey, this interface I want to change, I can tell that this affects these 2 other systems, and you know exactly who to go talk to with that. So a lot of that is just capturing a lot of the stuff that the engineers already know, or talking to all the people. You go talk to the electrical people and see what they have in mind, and the software people what they have in mind, and the manufacturing people what they have in mind, and the software back end, front end sort of folks what they have in mind, and making sure that everyone has the same clear picture of what we're building and how we're building it, because otherwise it's really easy to lose track of that stuff. And when you go to integrate everything, that's where you kind of get tested on whether you did everything right. And that's why all these bugs tend to pop out at integration, because that's where you start clicking the pieces together, and any mistakes you had in understanding how these work ends up having this sort of big, hard to troubleshoot integration problems that anyone who's worked on a really big project knows how it goes.
Yeah, I remember the scenarios where we needed to estimate like how much the integration effort will take, and usually, if we had a formula where like it's exponentially, the time needed for integration is exponentially growing with the number of participants in that project, or the number of components needed to be integrated. So that kind of speaks to this. Is like, if you have more components that talk to each other, the integration part will be, exponentially more difficult, let's say, to do rather than having a lower number of services or whatever needed. So yeah, but then if you have something in place, what you said, like system engineering, and hopefully keep the whole team aligned throughout the project, then you can reduce this down to some more reasonable effort, let's say.
Yeah, it's interesting because I've worked with teams that do the super traditional waterfall, like let's plan the entire product before we write the first line of code or pick the first circuit. Or I've worked with much more like internet and software driven teams who will go, it's totally agile. We're going to start with nothing and we're going to iteratively approach that. And yeah, I found that I tend to like something sort of in the middle, in that you build that it makes sense to do a little planning up front.
Yes.
Of going, okay, well, let's make the like cardboard version of our thing first, so we can take a look at it, and then move from there. So like, I tend to do a little bit of upfront planning of like, okay, let's look at all the things that we think we're going to have to do, and especially when you have a product that, or for electronics, it tends to be a little bit easier to work in that regard, because you go, well, what is my thing going to do? Is it going to have GPS on it? Is it going to read temperature? Is it going to have a cell phone modem or Wi-Fi or whatever? And you start breaking it down into pieces, and you end up getting sort of the categories of problems you're going to have to deal with, of like, oh, I'm going to have to think about battery life, or I'm going to have to think about how accurate is my sensor, or how am I going to build this? Or is one of these things, are some of these things really easy things that I've done a bunch of before, or am I using some new library or piece of hardware that I've never used before? So there's some risk there in terms of like, how long is it going to take me to get it actually going? And usually you shake out things where you go, well, I know we're going to have to do this. No one said whether we have to do this or what our performance numbers are going to be, or because the product specs will just say as good as possible or as best as possible, where you can put the first rough draft down or a prototype or something like that, where you go, okay, well, in an ideal case, we can get 100,000 samples a second or whatever. We know that, and that's doing nothing else. So we know we're going to be below that number. Is that good enough? Oh, cool. Turns out like 10,000's good. So we're good to move on. Or at that point you go, nope, we need 1 million, which means we have to change the hardware that we're using, or the approach or the design or something like that. So essentially, for me, planning means breaking it down into like the cardboard boxes of the stuff that you're going to deal with, and then the stuff where you go, that part makes me nervous, or I don't even know enough about that part to know whether I should be nervous or not. And then sort of iterate from there, because if you try and do everything waterfall, you could have missed those assumptions at the beginning, where you go, oh, this will all be fine, and then you don't build that component until 90% of the way through the project, and you go, oops, now we have to change everything, because this, or we have to, re-architect the system to isolate this component because it's changed pretty fundamentally from what we thought about, versus the totally agile approach, where you just kind of keep building, but sometimes it can feel challenging to know where you are and how close you are to done and things like that. Whereas looking at it sort of like, okay, today we've designed the cardboard version. Let's build towards that. Okay, that worked pretty well. Let's make it a little bit more robust and make the wooden framing version of it. Cool, that went pretty well. Okay, now we can start doing the metalwork and fab. And I read a pretty cool article recently that described bridge building. The first step of bridge building is doing what's called false work, where you build like sort of the 2x4 frames across the bridge, and that's what's going to support the bridge structures until the bridge is strong enough to support itself. And I actually really like that idea of like, well, like I can only build what I can imagine, and today I can imagine the wooden frames across the river, but that will make me in a position where I can then walk across those wooden frames and go, okay, but what does the bridge really need to be? Or, oops, we didn't notice, but halfway across this bridge, there's a lot of wind that we didn't notice before, and maybe we need to update our design to deal with that or something like that.
I really like this analogy. I think I used it also as well. The shortcoming of this is that, once you build that frame that kind of looks like a bridge and it almost has a function of a bridge, sometimes people may assume that the bridge is done. So I fell into these traps before. So I'm not sure how you deal with it. With this, have you seen this before?
Yeah, I mean, company and engineering culture is a hard thing to
Yes.
to build progressively. And I've worked with some clients where they have a good understanding of that, and I've worked with other clients where, like you said, the first time you have a prototype, they go, "Great, we're 90% done," and you go, "Nope, that was I'm gonna have to throw that one away." But this is a good sign that we're not like in entirely the wrong part of the world here. But I don't know if there's a lovely way to get over that. At least as a consultant, you have the nice benefit of, hey, you're paying me to be here. You brought me in because you trust my opinions, or hopefully you trust my opinions. And so when I say like, no, we need to think of it like this. And you know, working with good managers usually is a continuous talk about like, how risky are things right now. Where you say like, you know, the best managers that I've ever worked with think a lot about risk, where you say like, well, here are my three choices. They might have these engineering benefits one way or another, but they also have these risk benefits. Perfect. And when I talk about risk, I'm usually talking about time or effort and cost to implement and stuff like that. Software is weird where like it costs, well, manufacturing costs nothing, but development is massively expensive compared to other things. So,
there's like a zero marginal cost for software development, which is like, you know, mind blowing in terms of the standard engineering. But the NREs are huge. The non-recurring expenses are huge because you have to pay expensive developers to build this stuff. But the recurring expenses, stamping out 1 million instances of this, is zero. So you get this weird boundary where it's sort of like the opposite of when you think of like old school electrical manufacturing, where you go, well, look, I don't care if it takes you 6 weeks to figure out how to lower the per unit cost by 10 cents, because we're going to make 100 million of them. And that means that you're saving a couple million by spending those 6 weeks, where like the recurring costs greatly outweigh the non-recurring expenses. But software is totally different. And this is an interesting thing, especially when you're dealing with people who have traditionally managed electrical engineering practices or things like that. Or when you get the people who are from a software background and they try and start doing embedded or IoT stuff, and they have their simplified version of the calculations burned in their brain, but it's totally different when it comes to like manufacturing and hardware costs and things like that, where it's not that one's better or worse than the other. It's just, if you go into a new arena and assume you have the knowledge from a different arena, I've seen a lot of IoT companies get burned by that, by thinking that the IoT is still software only sort of a practice. Yeah, we talked about these iteration cycles in hardware and software and all that stuff. Yeah, definitely. I don't know, Dan, so you have any questions? I wanted to talk about Rust, but let's hear you guys out if you had something.
Let's see. No, I like the discussion so far. You know, I was thinking about the story you were telling about going from avionics to to startups and things like that, and taking the taking a different approach from waterfall into iterative like sprints and things like that. Something I was thinking of while you were describing that is, do you find that a lot of so-called engineering work is actually really fleshing out these more detailed requirements, where it's not necessarily just taking requirements and implementing them. It's actually sort of defining them and really getting it to a detailed level that you can move on to the implementation, sort of more so than just we think of iteration as like writing code and writing more code and that kind of thing, but maybe iteration is actually more about really defining what these detailed requirements are for the overall system, right?
Yeah, I mean, so with the disclaimer that I'm sure that there's just as many ways of doing engineering as there are people doing engineering. At least what I find is definitely like what you said, in that the development process isn't just, okay, I need to build this many lines of code. It's very much an iterative process of understanding the actual challenges that you're solving, because at the sort of macro business level, the challenges that you're solving are guided by customer requirements, or if you're in avionics, sometimes there's formal specifications of what a certain piece of equipment needs to do. But once you start zooming in into those boxes, the challenge is, how do you solve all those little pieces, and how do you produce a system that can give you the output that you want? So I definitely think that how you think about in most complex problems that I've tackled, the way that I think about the problem on day one is not at all how I think about it when we've actually solved the problem, in that like that development process is a continual improvement of the model of how we see the system, where we see these requirements is essentially a description of the system, and that does get iterated over time, which is why I don't so much love the waterfall approach, because you learn so much about the problem domain that you're working on, especially if it's not one that you've delivered exactly or very close to before. You know, the more changes you make, the more you're going to have to explore the space and how you can make those kind of engineering trade-offs to say, well, where can I steal a little bit from this column to make it fit into this column so that I don't need a bigger chip or more software or more RAM or a bigger battery? You know, it's all about those engineering trade-offs, and feeling out the system and what it really does need and what it doesn't need is definitely something that you get successively closer to as you get to the end of the project.
And what I also
it seems like, you know, that should be, or is, you know, is really the role of the developer too, you know, not just writing code, but really, you know, understanding, you know, what needs to be done, or what at a more detailed level the system, you know, it should actually be, right? So
yeah, and on top of this, what I like is like capturing those decisions and capturing this kind of like a transition through this journey. You know, through what you mentioned, like just using Git, for example, or whatever, is that you get to this kind of like a compounding effect where you started with some assumptions and like a card box or whatever, and then you iterated, and then each iteration is building on top of, you know, something that has been tested and so forth, and you get to some extent where you actually have like a vast amount of knowledge about that system, and then moving things around or doing some additional work is like becomes much easier, and with the higher velocity, right?
Yeah, I think there's one thing to capture the state of a system, but, you know, people are really good at solving problems and understanding things. So, I mean, there's a huge amount of that to having everyone be able to hold that model of what the system is supposed to do in their head, and being able to then very easily reference things where they go, oh, I don't remember exactly all of the packets that we send to the back end, but hey, we have this document that says when we send all of these packets, oh, this one doesn't have the kind of data that I expect it to in it. You know, I can go and validate that, where certainly you could take someone, you know, I've brought new people onto teams and things like that, and the docs help a lot, but there's also sort of that, yeah, like you said, the people who have been working on that challenge for a while start thinking in a way that helps them solve that challenge better. And that's sort of the benefit of how dynamic people can be. But there's a lot of just the mental model of thinking of solving a problem that develops over time and is not to be understated, I guess.
Cool. Yeah. Awesome. I don't know. I actually really want to talk about Rust on embedded systems. Something that I remember back in the days. What was it? 2015 maybe. That you know, people started talking about Rust on embedded systems, but I never jumped on that train, and I know you did. So maybe you can just brief us in on like how would that work, and like why Rust over like C, C++ or something like that. I know switching gears, but I'm curious about this topic.
Yeah, I'll give sort of a condensed history and hopefully cover my history and a little bit of Rust at the same time. But let me know if you have any questions. But yeah, so before we were working together, actually at the previous company that I worked at before we worked together, I was reading some internet news post or something like that, and it was something around the time when Rust was coming up to its 1.0 release. So this would have been like maybe late 2014, early 2015 or something. And I was reading about it, and it was this language that apparently had come out of Mozilla, and they were building this new language to get away from the sort of problems that Mozilla had when building a browser. Things like memory safety, or dealing with things like buffer overflows, or thread safety when you've got multiple threads, because back in the day, browsers were single-threaded, and then as PCs got more and more powerful by having more cores and things like that, browsers need a lot of resources, and so being able to utilize multiple cores is pretty important. But when you take a system that was designed with a certain assumption, like only running on a single CPU, and then go towards, hey, we're going to have multiple threads working at the same time on different cores, and well, we still need to share that data. What used to be a single-threaded problem, where maybe whatever we were doing was fine in single-threaded, but not so much okay in multi-threaded, Mozilla was seeing tons of problems. So this is before Rust started at Mozilla, sort of before 2011 or so. So it was even before the days of C++11, where things did get a lot better. But even then, they were still having problems despite code review, despite testing, despite all of these things where you had bugs. And sometimes those bugs turned into software exploits when you have things like buffer overflows or data races between threads. You can get to a point where you can trick the system into doing something it's not supposed to do. And when you have something as important as a browser, that can be a security problem and leak things like private data, or even be used to crash your computer or whatever, and things like that. So Mozilla kind of at the time went, one of the engineers working there went, okay, well, I have this idea for a new language, and the goal here is to make it so that it's as easy as possible to correctly write thread safe and memory safe code. And that how they solved that problem changed a lot between 2010 and 2015 when I read about it. But when I read about it in 2015, it was pretty close to the design we have today, which is a compiled language built on top of LLVM. So similar to Clang or Swift or other languages like that. They use LLVM as sort of the fundamental base of the compiler. And it was aimed to be a compiled language where there's no garbage collection or runtime or anything like that, which means it's suitable for writing high performance applications, or applications where you really need control over the kind of things that you're doing, while also making some fundamental changes that C and C++ don't have, basically making the compiler smarter in a lot of ways and making some of the rules more strict, so that you can't accidentally have cases where you have data races or memory unsafety problems like buffer overflows and things like that. And I was reading that blog post and I went, wow. At the time I wasn't working in avionics, but I was working in gas detection, which is another safety critical area. But I read that article and I was like, wow, if they deliver on what they promise in their marketing material, that's going to be the next thing for safety critical in like 5 or 10 years. Like, those industries move slow, but if they're actually delivering on the things that they say they're going to deliver on, then that's going to be the thing. Because I've experienced all of those problems in developing safety critical C code in the past, of no matter how much formality and practice and, be really good you are, stuff happens. Like, pointers are, well, I don't know. Working with a lot of those low-level things can be very challenging to keep perfect, and just one mistake can mean a crash or a vulnerability or things like that. So I started learning it then. I'm sure I talked about it a lot when we were working together, but didn't really start using it until sort of the very end of that job. But around that time, probably 2017, 2018, Rust had been around for 3 years. So it went 1.0 in 2015. And at that point, because it was a compiled language, and because LLVM through Clang supported embedded targets, because I think probably Apple is using LLVM and Clang for developing bare metal software and things like that, it was totally possible to compile and run Rust code on bare metal, like microcontroller systems, areas where you don't have an operating system and things like that. And but the thing is, it wasn't easy. Like it
Yeah.
was you really had to sort of reach into the guts of the compiler and tweak a lot of things that weren't designed to be tweaked necessarily to get it to spit out a program that wasn't expecting that it was on Linux or things like that. So around that time in early 2018, the Rust compiler team has these sort of, or at the time they had notions of what are called working groups, where they go, look, something sucks today in Rust. So the people who are interested in it, you're the working group, go figure out how to make it better and suggest changes to the compiler and things like that, and work on building out libraries and things like that to make that not suck. So a guy named Jorge reached out to me at that time. He was much more active in the development of the compiler, and I had been doing some prototyping, trying to get some code working very painfully on bare metal embedded systems. And he reached out to me and a couple other folks, and we got the first group of the working group together. And basically our goal was, by the end of 2018, we want it to not suck to do bare metal embedded development in Rust. It shouldn't be painful. You shouldn't have to follow a 60-step wiki of all the dials you have to tweak to get things going. And by the end of 2018, we had it to the point where it was about as easy to build and run an embedded binary produced in Rust. It was about as easy to build an embedded binary as it was to run a desktop program. We built out a lot of the support libraries, like how do you boot the system up and get from the reset vector on the microcontroller to main, and then how do you build sort of portable libraries where if you write a driver for a GPS receiver that takes serial data, how do you make it so that you don't have to rewrite that driver for Nordic parts and STM parts and whatever things like that? How do you just say, well, you have a serial port, how do you write a driver that can be used on any piece of hardware that has a serial port? So all of those kind of things, working on sort of the infrastructure of that and getting those changes into the compiler itself. And it wasn't me. There's a lot of other people working on that, but also working on the things like documentation of guides or books, as they're usually called in Rust, of how you do this and how you learn, like if you're coming from C or C++, how you learn how to do embedded Rust. So by the 2018 edition, so Rust has editions, which are kind of like C++ has C++ 11, 15, 17 or whatever, or 14, 17. Rust has editions. So 2015 was the first one because that was 1.0. 2018 version of Rust was sort of the second major iteration of the language. And in the 2018 edition of Rust, it was now stable or guaranteed to work, that you could build and run your embedded applications there. And so sort of fast forwarding from there, at that point I was working at a company using embedded Rust, but realized that sort of out of all the industries that Rust worked with, whether that was back-end applications or whatever, embedded was the area where the status quo was the worst, in that like there's no standard tooling or very little standard tooling on building applications that work on different platforms or writing portable code, or just being able to take what you wrote yesterday and use it on your project tomorrow. Because there was this huge gap there, and from the interest that I had seen from working on the working group, I went, well, I'm pretty sure I could, there are some people who are definitely willing to take this up now. As early as it is, there are some folks that are seeing the benefits and are willing to take it up now. So I met up with some other folks here in Berlin who had also been working on Rust for a number of years, and we started up a consultancy called Ferris Systems, where we just did Rust consulting. And we sort of assumed that embedded was going to move slow, and it was going to be our slowest business area, but we'd keep, moving that field forward while consulting on web and back-end stuff or other high performance or high control areas where Rust works really well for. But that's not exactly what happened. We ended up having a ton of embedded interest. And ended up being, cool. After 2 or 3 years, embedded ended up being sort of like our biggest business area. Nice. And so I spent a lot of time working on embedded stuff and training up our team and building a team to do embedded stuff, and working on a lot of bare metal or very low level of control embedded-ish Rust things. So over the course of sort of 3 years, we went from it not really being stable to we could sustain a 20-person consultancy on the amount of work that we were doing in embedded Rust.
Cool.
A lot of training, a lot of, like I said, these first proof of concept projects and things like that. So Ferris is still doing some very cool things. They're working on a safety critical version of the compiler because there's a lot of embedded industries, like automotive is a big one where they can't just pick up new things necessarily. They need some sort of approved tools, and I could go into that for a very long time, but basically working on a version of the Rust compiler that checks those boxes that you need to check in safety critical industries and stuff like that. So I left there at the end of last year. I've been doing solo consulting for the last year or so. Like I said, some of it's bare metal development, some of it's advising, some of it's a lot of different stuff, but helping folks that I know out on a lot of interesting problems. But why Rust, I guess I didn't answer, but like I said, the challenge was you could do a lot of these things in embedded, and people have certainly shipped working embedded systems for decades in C. But there's always sort of like, for me, there was always sort of just an egregious pile of paper cuts that didn't need to be there. Stuff like you have to know exactly how to get the compiler to do certain things, or it would just silently not work. Or you have to know the conventions of how registers work and how to invoke the language to make it work with those things. Or you always expect that you're going to have to rewrite a library because someone wrote it for an STM32 and you're running it on an NRF52. And certainly there's been iterative approaches to that to try and address that in C. There's things like Arduino, which go from a very high level of a version of C++ with basically standard patterns, and you get interoperability from the highest level of abstraction. Then there were things like Platform IO, which sort of built on, I think, originally the Arduino stuff, and now they have their own thing, I think. But solving some of those problems of, hey, I have a bunch of this code, how do I get it all to build? And I have these external libraries, how do I get those to build? And, oh, I'm doing this on a different CPU today than I was doing before. And Platformio address some of those. Nowadays, Zephyr is probably the biggest effort I see of trying to write, portable code and things like that. I think I heard Axel describe that as, how did he describe it? Yocto for embedded, which I think is a really interesting approach. But the thing is, Rust has a lot of both tooling powers and language powers to get a lot of like fundamental safety things right, like make sure that you always configure your hardware in the right way, as well as build tools that make it really easy to just debug and run and log your firmware. So it's one of those things where it was easier to build better tools in Rust than it was in C, which made me more productive and get things right quicker, despite the cost of, for me, the cost was building up or helping to build up the ecosystem because it didn't exist. But even for people today, the cost trade-off there is, am I going to spend some time learning Rust, the language, and then how to do embedded Rust? And, obviously I'm working with clients who say yes, but
I was about to ask, so I'm looking at this, there is like Rust embedded on GitHub and then embedded HAL as well. So, but do you think now this like hardware abstraction layer in this like working group, it's at that level that actually if you know Rust to some extent, that you might be more productive by developing like applications in Rust, productive plus having that guarantee of like buffer overflows and all that stuff. So is this at that point now that it can be safely kind of recommended and used?
Yeah, certainly. I've been doing it for years, but I am certainly the most biased person that you could ask. But it's to the point where it is possible to sit down and say, okay, look, I found this off the shelf. Rust has libraries called crates, which are in a package manager. You can literally look on there for embedded drivers, like, oh, I want a display driver. Cool, I found a display driver that works with my specific e-paper display. And then there's also this graphics library in Rust. And, oh, look, there's also a driver for the NRF52 that I'm using, or whatever one of the 10,000 STM32s flavors that are out there. You go, okay, well, the STM32 has a driver that works with SPI, and my display driver will take an SPI device and give me something that I can use to draw on it. And then I can plug my graphics library into that, and it works. So you can really sit down, start a blank project, add your dependencies in, plug them into each other, and then in like 15 minutes have a working e-paper display. And embedded HAL is a really cool abstraction of sort of taking breaking down communication protocols like SPI or UART or I2C or whatever, and saying like, what's the common denominator there? Because most drivers only care about like, okay, you need to toggle the chip select pin like this and send this many bytes in this endian this order or whatever. Where there's a lot of commonalities across these chips, even though their hardware is very, very different. In embedded, everyone wants to control everything down to the very last, register setting. So, I mean, the embedded HAL or these abstractions will probably break down if you're trying to do something really, really painfully specific for optimization or power usage, things like that. But unquestionably, the abstraction layers are the best starting place, and you can always just take that code and refactor it into exactly the sort of challenges that you're facing.
Nice. Excellent. I actually wanted to open up for questions. I think, this is really interesting. I think we can talk for hours about this, but I wanted to see if there's anybody who has some questions that we can drill in specifically. So if you do have questions, raise a hand. I'll probably see it here, and then we can talk about it. Otherwise, I don't know, Dan, Syed, you two guys have any questions?
Yeah, I have another question. So how do you see the state of Rust today? It sounds like things are all possible. Do you do most of your Rust embedded development bare metal, or are there some RTOSes or things that you can use in combination with Rust? I know that I've seen some work with getting free RTOS to work with Rust with some mapping libraries and things like that. But kind of curious where you see the state of things today, and actually where you see things going.
Yeah, so blending languages. So Rust has a really good FFI story, or foreign function interface. So because they are both compiled languages, at the object code or binary level, there's really no difference between C code and Rust code from the CPU's perspective. And the Rust compiler has a way to work natively with C. So you can create a Rust library that is a static library that has C function signatures on it, and you can call into it. From a systems perspective, the more different areas you have can make the project more complex. Like if you're in this part of the code and you have to think in C, and you're in this part of the code and you have to think in Rust, and at the boundary layer you have to think in both C and Rust, that can be a challenge because C is just less strict of a language than Rust, which means it's very easy for C to say, yeah, I got this, and Rust to go, okay, well, you got this, and then, breaks one of the rules that the Rust compiler would usually stop, but the C compiler has no problem with. So there's always sort of a cost of whenever you're mixing library or languages, and this would be the same as if you were doing, let's say, low-level drivers in C and then a scripting layer in Lua or Python or something like that. There's sort of always that cost of having to understand both systems, particularly when things don't work the way they're supposed to. But I've absolutely helped folks before with, for example, building a Rust bindings to some standard OS things like FreeRTOS, or there was another one that I did, but I can't remember off the top of my head, but we'll use that as an example of being able to call these C functions in the same way, or building a very thin sort of native Rust layer that does all of that checking whenever you go across the bridge and do those kind of things. And for folks who say, well, I have this one really sensitive task on FreeRTOS that I do want Rust to have, or there's a Rust library that I want to use. It's certainly possible to create have Rust build a static library, add that into your CMake target or whatever, so that it gets linked in properly, and generate the headers that go back and forth between those two kind of things. I tend to help a lot of projects that are just using Rust. I find that a lot of embedded folks, they'll usually start with the off-the-shelf components. I think Zephyr is sort of a newer thing that it does have sort of higher qualities of expectations versus maybe 5 or 10 years ago. If you were just pulling the vendor demo code, I'd say most people would probably expect to rewrite some or all of that anyway. So for a lot of applications where they need specific things. So I'm helping a lot of projects that are starting with Rust from scratch, just because they're looking for sort of those total system guarantees. But there are certainly folks who are not doing that. And for folks who have a huge amount of time and money and effort sunk into supporting a platform, it's a much more challenging choice to say, hey, we're going to rewrite that all from scratch. That's a very, it's a tall order, and it's certainly possible, but I can certainly understand not everyone wants to or can do that. So a lot of the folks that I've been helping are either, like I said, doing a new iteration of a project where they do have to change the CPU. Like, let's say the last one was on either some very old Cortex-M or a PIC 16 or something like that, and they're moving to a Cortex-M. So for them, there's not a lot that they can carry over anyway. Or folks who are doing a fairly targeted area and things like that, where they say, look, we just need one library that's very reliable, and it won't necessarily talk to all of the system. Like, it's not going to talk with the hardware and whatever, but it's keeping the state of the network protocol going, or it's doing serialization and deserialization just because we need that aspect to work. So for bare metal folks, that's what I've been doing. I also right now I'm working with a company that does more scientific equipment type stuff, but it's on a desktop class CPU. It's running an operating system. So I am writing all Rust there, but it's not all the way down to the operating system level, but they're looking to move to Rust because it has higher performance and plugs into a lot of other ecosystems as well. So where it is right now is basically, if there's someone else if there are drivers out there for a lot of things. Not everything will have a driver. If you're using a fairly specialist sensor or CPU or things like that, you might end up needing to write drivers for that and things like that. But that's something that generally with open source the list is growing longer all the time. And the documentation for if you do need to build it yourself from scratch is fairly good. And I'd say I'm certainly to the point where even with 10 years of experience in C and maybe 6 years of experience in Rust, I'm way faster to build something that works the first time with Rust, because I sort of can, it's the way my brain thinks now. And I certainly think that is possible for a lot more folks than just me.
I'm looking at this like ESP32, and I see that they have like the ESP hull, and then they are using the embedded hull underneath. I mean,
yeah, they're really cool because they've done two things. So ESP32, Espressif is the first company that I've seen that sort of has public official support for Rust in their SDKs. So they have that ESPRS organization, and they've sort of come at it two ways, where normally in bare metal Rust, you don't have access to the standard library. Rust has a pretty good delineation between these are the parts of the standard library that don't require an operating system, and that's called core. And then there's the part of the library stuff that does opening files and sockets and stuff like that. That's in the standard library. And normally when you're on a bare metal system, you don't have the standard library because you don't have an operating system. So there's nothing to provide file systems and network sockets and things like that. But the ESP32 is already built on top of FreeRTOS, which means they have an OS. So rather than try and build out sort of a bare metal style library for Rust, they've actually built a version of the Rust standard library that talks to FreeRTOS as if it was the Linux kernel, for example. So you end up writing applications there that feel like you're running on Linux, but you're running on a bare metal system. And they will have some other limitations, like maybe FreeRTOS only supports so many files open at a given time, or so many network sockets open at a given time, and things like that. But they've built sort of the ESP HAL to be on top of FreeRTOS as an underlying kernel, more or less. They also have another one, I don't remember what it's called, but where they've done not that, where they say, okay, this is if you want to drive all of the hardware yourself, and you want to write something totally bare metal without FreeRTOS, which originally was a big challenge because their Wi-Fi stack was all really tightly integrated into FreeRTOS, and I think they are actually working on factoring that out. But I think it's also a really good example for folks that have a working, stable system and want to build something practical on top of it with Rust, is to treat it as if it was, sort of below the world that you care about.
No, that's
Very cool.
That's pretty cool.
I've just got a quick question. So, I mean, you have played with C as well as Rust, right? So, I guess my question would be, have you actually had a chance to benchmark a code written natively in C and written natively in Rust to benchmark from the footprint perspective and performance perspective?
Yeah, so this is one of those things like statistics where there's lies, damn lies, and benchmarks.
Yes.
So I mean, like, benchmarks are one of those things that are hard, but I mean, like I said, it's still being compiled by the same base compiler, like LLVM. So Rust generally compiles to a speed and size that is comparable, typically between what you would expect from C and C++. There's some areas where Rust can be faster and smaller because the compiler knows more. You can have stronger guarantees where you don't need to do things like defensive bounds checking because that's checked at compile time, not at runtime. So there are certainly areas where, and there's some work on some things like, if you've ever heard of the restrict keyword in C, there's some ability to tell the compiler, hey, I'm not reusing these pointers, or this is guaranteed not to be this. And this is generally the reason why Fortran is so fast at math code, because its compiler makes some of these non-aliasing guarantees, which is how Fortran manages to outpace C or C++ in a lot of mathematical things. And because Rust is similarly strict in what you can't do, it can make some of these optimizations, and some of those are being enabled in the compiler. What happens when we turn them on in the compiler in LLVM, we found out that turns out no one really practically uses restrict. So even though it's in the C language and you're supposed to be able to do it, causes all kinds of compiler miscompilations and stuff like that. So this has been like a 3 or 4 year process for Rust to say, hey, wait, LLVM, you need to fix all of this stuff that you said you can do. And it turns out we're the first one to really use it at scale. So there are things like that where the compiler is getting faster or the produced compilation code is getting faster on every release of Rust because they're working through these things. I mean, from a high level, you can build, I think for the Interrupt blog a couple years back, I built a 0 to main in Rust, where I think it was like 400 bytes for a hello world that blinked an LED, like, delay cycles and blink an LED or something like that. So, I mean, you can get it down to as small as you could probably get C in those areas.
Yeah, one of the things that, I kind of like think this through is, so, if somebody's coming from C and fully understands, like always thinks C and assembly and how like that is connected to each other, and like he writes C as that understands like what the actual code will be produced. I mean, that will always be, more optimized. But with Rust, you also have like a lot of abstractions on top provided by like different cargos and different packages that come in, and like a lot of high level, let's say, languages that use this kind of functionality. And then you might just be like, oh, that's fine, I'll just use those and then produce a huge amount of code that actually, at the end might not, or it will do what you want, but it will not be as efficient, let's say. So I don't know what you think about this. Have you seen that pattern occurring?
Yeah, so one of those things this is one of those, like, people say it, but I disagree with it super hard, is C is portable assembler. And that hasn't generally been true since we've been programming on PDP-11s, because this is what a lot of people forget. And when they get into the realm of what is undefined behavior and stuff like that, is that you're not writing C as if it was portable assembler, and compilers don't expect you to be doing that. And that's why so many folks get bit by undefined behavior or implementation specified behavior and stuff like that, is that your target is not the CPU you're targeting, it's the C abstract machine, which is totally different. And so it's definitely one of those things. But to go back to your actual question, Rust does provide a lot of things like iterators, and has sort of functional patterns where you can do things like map and zip and take multiple iterators. And there was specifically a PR in the NRF52 HAL, which I worked on, where I had written the original HAL implementation for the SPI port in a very like old school C for loop, iterate the index, because you know, thinking of what the assembly would be, and
Exactly,
I was like, oh great, it'll be fast, and I ran it and it was okay for a while, and then I went back and rewrote it to use functional combinators, things like iterators, and it ended up being smaller and faster.
That's pretty
Even
cool.
though I was
That is
writing what
pretty cool.
looked like you know, fairly intricate code of, hey, we're gonna tie these two iterators together, and then until one of them runs out, we're gonna do this, and then when one of them runs out, we're gonna do this until both of them are out, and those kind of things. But in Rust, because when you use an iterator, you know that you're never going to go out of bounds of an array, which means you don't have to do bounds checking, because it knows that it's going from, let's say, 0 to 20. So you don't need to, whenever you're like subscripting into an array, you're not doing bounds checking. So it can often optimize way better, because in Rust you typically describe what you want to be done, and then the optimizer just kind of goes, okay, well this is how you do this the fastest.
That's pretty cool. That's pretty cool.
So I mean, certainly in head-to-head things, I have had cases where writing what feels like idiomatic Rust code be faster than what it feels like the portable assembly should be.
Nice. So you trust the machine rather than, you know, your instinct. So that's kind of like, yeah, pretty good to have. Awesome. I think we kind of ran out of time. I don't know. Let's see if there are any other questions perhaps that we can take. Otherwise, we can just start closing it down. So I don't see anybody raising a hand, so I assume, yeah, they not have any questions. Anything you wanted to, for the end, say, or like, I don't know, what you're working on, or where can people find you, or that kind of stuff? I will put all the links that we talked. I kind of collected the links that you were mentioning, even the book. And then I'll create a post afterwards that we can reshare, so that people can reference apart from just listening to this, because I think was a lot of information, at least for me. But yeah, anything you want to add as a closing words?
No, yeah, you'll link a bunch of stuff. I have my website. I'm most actively writing on co-host these days. Feel free to reach out. My email's on my contact page. Whether you're just interested in Rust stuff or systems engineering stuff, or you have a specific challenge and want to see if I can help out with that, I'm certainly doing consulting these days, so I'm more than happy to chat with people or point them in the direction. There's a lot of good. I'll send you some links to like the Rust embedded space, where there's like the awesome embedded Rust list, which is people's projects and libraries and stuff like that. Cool. So if you want to get a feel for what's out there, there's that, and a lot of teaching material. But yeah, it's been awesome to talk to you, and good to talk to you again after a while. Yeah, excellent. Yeah, same here. Okay, guys, then I think that's it for today's session. Thanks everybody for joining. And then James, really appreciate you taking time to kind of talk with us. I think we have left like quite a lot of topics that we wanted to chat. So I think that will be an opportunity for us to connect one more time, maybe next year. Definitely. So, yeah. Okay, cool. Then Syed, anything from you guys before we close? Otherwise,
nope. Thanks a lot, Nenad.
Yeah.
Thanks, James.
Okay, thanks everybody. Then that will be for today's show, and then we hope you tune in the next Wednesday one. Actually, we will not have. Then, do we have the next Wednesday? No, because I think that will be.
I think this might be the last session for this year, actually.
There you go.
I think we'll take at least another 2 weeks hiatus here, and talk to you in 2023. Yeah, next year. So okay, cool, awesome. Then tune in next year, and then I wish you good night or good day, whatever timeline you are at. So goodbye.